A single neutron drifts into a uranium atom. Nothing about it looks dangerous. No flash, no sound. Just a tiny particle slipping into a crowded nucleus. And yet, in that quiet moment, something irreversible can begin. One atom splits. That split releases more neutrons. Those neutrons split more atoms. 2 become 4, 4 become 8. In less than a millionth of a second, a calm piece of matter can turn into a runaway storm of energy. Robert Oppenheimer once said this simple multiplication was the heart of the bomb. Not fire, not force, just a chain reaction that refuses to stop. 1. The quiet atom. When you look at a piece of uranium, nothing about it tells you what it's hiding. It sits there, heavy, dull. Just another metal. But inside every uranium atom, there's a disagreement that has never been resolved. You have 92 protons squeezed into a space, so small it almost shouldn't exist. Every one of them is positively charged, and every one of them is pushing every other one away. If electricity were the only force at work, that nucleus would explode instantly. The only reason it doesn't is because the strong nuclear force is pulling them together even harder, but only across very tiny distances. So what you're really holding is a loaded spring. Now picture a neutron drifting by. It has no charge, so the electric forces don't even see it. It can slip straight into that nucleus like a ghost walking through a locked door. When it does, it nudges the balance just enough to let that spring unwind. The nucleus splits. And when it splits, something strange happens. Those two fragments are both positively charged. They finally get to do what they always wanted to do, repel each other. They blast apart, and in that blast you get energy. Not from burning, not from chemistry, from electric force that was trapped and suddenly released. You also get more neutrons. That's the part that changes everything. 1 neutron goes in, 2 or 3 come out. Each of those can go on to do the same thing to another nucleus. And if the conditions are right, the process doesn't slow down. It speeds up. 1 becomes 2, 2 become 4, 4 become 8. This is the heart of a nuclear reaction, not an explosion, a multiplication. And once that multiplication gets ahead of the material holding it, there's no way to put it back. 2. Oppenheimer, the translator of chaos. By the time Oppenheimer walked into Los Alamos, physicists already knew most of this in pieces. They knew neutrons could split atoms. They knew fission released energy. They even knew chain reactions were possible. But knowing something on paper and building something that depends on it are two very different things. Imagine being in a room with 100 brilliant scientists, each one obsessed with a tiny slice of the problem. One is thinking about neutron speeds, another about uranium purity, another about shock waves. If nobody ties those ideas together, you don't get a bomb. You get a pile of unfinished thoughts. That was Oppenheimer's job. He didn't just run the project, he taught it. He stood in front of rooms full of physicists and gave them a way to think about the entire system at once. Instead of drowning people in equations, he kept coming back to a few simple ideas. How many neutrons do you make? How many do you lose? How fast does the reaction grow? That was his genius. He reduced a nightmare of variables into something you could hold in your head. Other physicists could tell you what happens to a neutron when it hits a nucleus. Oppenheimer helped you see what happens when millions of those events start talking to each other. He didn't just explain nuclear reactions. He explained how they behave. And that difference mattered. 3. What a nuclear reaction actually is. So let's slow this down and make sure we're really clear on what's going on. When a uranium-235 nucleus splits, it releases energy and it releases neutrons. Those neutrons now have 3 possible fates. Some of them escape the material entirely. You can think of those as gone forever. Some get absorbed by nuclei without causing another split, also gone. And some strike another uranium nucleus and cause it to fission. Only that last group keeps the reaction alive. So if you're building a nuclear system, what you're really doing is counting. For every fission that happens, how many new fissions do you get in return? If the answer is less than 1, the reaction fades away. If the answer is exactly 1, the system sits there in a delicate balance. That's how nuclear reactors work. And if the answer is more than 1, the reaction grows. Fast. That's what a bomb is. A system where, on average, each split leads to more splits. This is why mass alone doesn't tell the story. A lump of uranium can be harmless if neutrons leak out faster than they can cause new fissions. But squeeze that same material into a compact shape, and suddenly those neutrons stay inside. They find more targets. The reaction tips over the edge. So when Oppenheimer talked about nuclear reactions, he wasn't really talking about energy. He was talking about balance, about whether multiplication beats loss, about whether the chain outruns the material holding it together. Once you see it that way, the bomb stops looking like a mystery. It starts looking like a very unforgiving math problem. Before we get into how Oppenheimer actually explained this to the scientists who built the bomb, take a second to like the video and subscribe. This channel is about slowing down big ideas until they make sense, and that only works if you're here for the long run. 4. Oppenheimer's way of explaining it. Now that you've got a grip on what's actually happening inside a chain reaction, let's talk about how Oppenheimer framed it, and why so many physicists even today find his explanations oddly compelling. Most physicists of his era, and many still, instinctively reach for equations and cross-sections when they think about nuclear reactions. You ask them about fission, and they start talking about probabilities, neutron energies, scattering amplitudes. Their minds go to layers of math that require careful calculation and simulation. Oppenheimer took a different tack. He didn't deny those things, he just didn't start there. In one of his post-war lectures, he said something that felt almost simple, but if you really unpack it, it's brilliant. The essential feature of a bomb is not energy release, but the rapid, uncontrolled growth of that release. A chain of events doubling on itself so fast that it outruns every attempt at restraint. He didn't talk first about cross-sections or differential equations. He talked about growth, about multiplication, about runaway, about timing. Here's the trick. He turned the problem into a story about balance. Not this. Here are the fission cross-sections as a function of neutron energy. But this. You're standing with a bucket of neutrons. For every neutron you lose, another must take its place. If losses outnumber gains, the system dies. If gains outnumber losses, the system runs away. That's a mindset you can hold in your head. You don't need a computer to picture it. And that's exactly what happened in Los Alamos. Oppenheimer taught teams of physicists, chemists, and engineers to think in terms of neutron economy, a phrase that sounds arcane, but to him was intuitive. How many neutrons stay inside? How many escape? How fast do they multiply? This was not just a mnemonic trick. It was a reasoning framework that let people predict what would happen without solving every equation from first principles. Compare that to the way other physicists usually teach nuclear reactions. You start with the math, then you derive the intuition. Oppenheimer did the reverse. He began with the intuition, and only then showed how the math supported it. And that order matters. It changes how you think about the problem, not just how you calculate it. A modern physicist might open a textbook, point to the neutron transport equation, and begin there. Oppenheimer would pick up a chalk and say, let's think like neutrons for a moment. Let's see where they go, what they need to survive, and what makes them disappear. That mental model of neutron survival versus loss, of growth versus decay, is what still resonates today. Not because the math is simple, but because the way of thinking is powerful. He didn't just explain nuclear reactions. He showed you how to think about them. 5. The nerd critique. Here's where we have to be honest with ourselves. Oppenheimer's way of explaining nuclear reactions is powerful, but it is also a simplification. A brilliant one, but still a simplification. When you say a chain reaction is just neutrons multiplying faster than they're lost, you hide a lot of messy physics behind that sentence. In the real world, neutrons don't politely fly straight from one nucleus to the next. They scatter, they bounce off other atoms. They slow down, they get absorbed by impurities. Some of them turn uranium-238 into plutonium instead of causing fission. Some simply disappear. Even the neutrons that do cause fission don't all have the same energy, and that energy changes how likely they are to trigger the next split. So when Oppenheimer talked about multiplication, he wasn't denying this complexity. He was compressing it. He was saying, all of those messy details ultimately collapse into one number, the average number of new fissions you get from each fission. That's a very dangerous simplification if you take it too literally. Real bomb design required thousands of measurements, tables, and calculations. Neutron transport theory is brutally complicated. Modern nuclear engineers use massive simulations to track what neutrons actually do. But here's the thing, none of that replaces Oppenheimer's framing. It sits on top of it. Even today, when you run a nuclear simulation, you are still asking the same simple question he taught at Los Alamos. Are neutrons being created faster than they're being lost? The computer just answers it in a more detailed way. So his explanation isn't wrong. It's just mercilessly efficient. 6. Why his thinking still matters. This is why Oppenheimer's way of explaining nuclear reactions hasn't faded. We now understand fission far better than he did in the 1940s. We know about delayed neutrons, resonance absorption, moderator effects, and 1,000 other details that were only partly understood back then. But when you strip all that away, the core logic is exactly the same. A nuclear reactor is a system where multiplication is carefully held at 1. A nuclear bomb is a system where multiplication is allowed to run away. That simple distinction still defines the entire nuclear world. When modern physicists model nuclear weapons or power plants, they use codes that simulate billions of neutron paths. But the output they care about is still something Oppenheimer would recognize. How fast the reaction grows, how long the material stays together, and how much energy is released before it flies apart. His framework wasn't just useful in 1945. It's still the mental scaffolding underneath everything we do with nuclear physics today. He taught people not just how to build a bomb, but how to think about systems that can destroy themselves by growing too fast. And that idea has never stopped being relevant. 7. The human weight of knowing. Once you really understand what a nuclear reaction is, not as a spectacle, but as a system, it becomes impossible to ignore how strange the responsibility is. You're no longer talking about violence in the ordinary sense. You're talking about arranging matter so that it does something it was always on the edge of doing. A uranium nucleus doesn't want to explode, but it is held together in a state of permanent tension. All you do as a physicist is tip the balance. You create a situation where the rules of the universe, followed honestly and without malice, run away from themselves. That's what makes Oppenheimer's role so unsettling. He wasn't a man who built a weapon by accident. He was a man who understood, in exquisite detail, why it had to work. He could see the chain reaction unfolding in his head long before any metal was machined or any explosive was tested. When he spoke about neutrons and multiplication, he wasn't speaking abstractly. He was describing a future that he knew would arrive the moment the conditions were right. There is something uniquely heavy about that kind of knowledge. A general can order an attack. An engineer can build a bomb. But a physicist like Oppenheimer knew exactly which laws of nature would carry that order out. He wasn't commanding people. He was commanding reality. And yet, the same way of thinking that made the bomb possible also made it impossible for him to see it as just another weapon. When you understand that a nuclear explosion is not fire but a runaway pattern, it stops feeling like an act of war and starts feeling like a breach in the fabric of how the world normally behaves. You're not just breaking things. You're letting the universe speak in a voice it almost never uses. 8. The pattern and the mystery. If you step back from all of this, the neutrons, the nuclei, the equations, the terrifying speed of it all, What Oppenheimer really gave us was a way of seeing. He showed us that even the most extreme events in nature are not chaotic. They are patterned. A nuclear reaction, at its core, is no more mysterious than a bank account. Do deposits outpace withdrawals, or don't they? Do neutrons multiply faster than they disappear, or don't they? And yet, for all that clarity, the deepest question remains untouched. Why do nuclei have this tension at all? Why does matter carry energy in this form? Why should a tiny neutral particle be able to unlock something so vast? Oppenheimer understood that physics does not answer those questions. It never has. Physics tells you how the pattern behaves, not why the pattern exists. It shows you the rules of the game, not who decided to play it. That is why his way of explaining nuclear reactions still feels so strange and so powerful. He didn't pretend that understanding the mechanism meant understanding the meaning. He gave us a clear window into how the universe works at one of its most dangerous edges, and left the mystery intact. We learned how to split the atom. We learned how to make it run away from itself. But the reason that such a runaway is even possible remains one of nature's quietest secrets. And maybe that is as it should be. If this helped you see nuclear physics from the lens of Oppenheimer a little more clearly, go ahead and like the video. It tells the algorithm that thoughtful science still matters. And if you want more stories where physics is explained in a more intriguing yet thoughtful manner, subscribe this channel. Our videos comes out every week, and they're built for people who like to actually understand physics the smarter way. Thanks for watching.